Hi everyone, this is Dr. G. Ravindranath Reddy working as Assistant Professor of Mathematics in MLR Institute of Technology, Hyderabad. So we are discussing numerical methods and integral transform course. In that course, we are at the convolution theorem in the Laplace transform. So in this video, we will see how to use this convolution theorem, when we can use this convolution theorem, what is the statement of this convolution theorem. All these things we will discuss in this video. So first we will take the definition here, convolution product. So for this I am taking the two functions f of t and g of t are the two functions defined, and this convolution of f of t and g of t is defined as f of t star g of t is equal to, so this convolution product of these two functions f of t and g of t is represented with the integral that is defined as integral 0 to t f of u into g of t minus u into du. That means we have to apply the integration with respect to u. So this f of t star g of t, we can read it as convolution product of f of t and g of t. So this star represents the convolution product of these two functions. F of t star g of t is equal to integral 0 to t f of u into g of t minus u du. So this f of t star g of t can also be written as f star g of t. Now we have some properties of this convolution product. So first we will take the convolution operator star has the following properties. We are having some properties which satisfies this convolution product. So the first property is commutative property. Suppose we can take f of t star g of t. So this convolution, even though if you take f of t star g of t, this value is equal to g of t star f of t. So this convolution product satisfies this commutative property, which is defined as f of t star g of t is equal to g of t star f of t. And associative property, you take three functions f of t, g of t and h of t. So this can be written as f of t star of, that means g of t star h of t. So this is equal to, first find out the convolution product for both f of t and g of t, and then whatever the value we get, you once again apply the convolution product of the third function, that is h of t. Both values will be same. This is associative property. And the next one is distributive property also. So this is our distributive property. The convolution product of g plus h, sum of the two functions. If we apply this one, this is equal to f of t star g of t plus f of t star h of t. So this is our distributive property. So out of these three properties, while you are using this convolution theorem, we can, in some cases we will use the concept of commutative property. So f of t star g of t is equal to g of t star f of t. So we will use this property while you are solving the problems. Now we will take the statement of this convolution theorem. So f of t and g of t are the two functions defined for t greater than or equal to 0. Then Laplace transform of f of t star g of t is equal to f bar of s into z bar of s. If you send this L to this side, you can take L inverse of f bar of s into z bar of s is equal to f of t star g of t, that is convolution product of the two functions f of t and g of t. So by the definition of this convolution, we can take this convolution product as integral 0 to t f of u into g of t minus u into du. So by using this convolution theorem statement, it is very clear that, so whenever the function f bar of s is a product of two functions which are in terms of s, then if you want to find out the L inverse of that product of two functions, then we can go to the convolution theorem. So whereas in the Laplace transform we don't have the facility to find out the Laplace transform of product of two functions f of t star g of t, but we have the facility in the inverse Laplace transform that is provided by this convolution theorem. So whereas in the inverse Laplace transform we can also find out the product of two functions f bar of s into g bar of s. Whenever we are having this type of functions, for that we can also find the inverse Laplace transform by using this convolution theorem. So simply we can say that convolution theorem is useful to find out the inverse Laplace transform of product of two functions which are in terms of s. So for this purpose we can use the concept of this convolution theorem. Now let us take the example here. So find L inverse of s by s square plus a square whole square by using convolution theorem. So by using this convolution theorem we have to find out the inverse Laplace transform of this function. Now whenever we want to apply this convolution theorem we have to take this function as the product of two functions f bar of s into z bar of s. So the first point what we have to remember is we have to split this function as the product of two functions here. So what is our function here? S sub by s square plus a square whole square. So I want to split this one as s sub by s square plus a square into 1 by s square plus a square. So once if you multiply these two, once again we have to get this value here. So like this, whenever we want to apply this convolution theorem, whatever the function he has given inside the L inverse, and we have to convert that L inverse of that function as product of two functions. So that is the point we have to remember here. So L inverse of s by s square plus a square whole square. So this can be written as L inverse of s by s square plus a square into 1 by s square plus a square. Now once if we observe this one, this is of the form L inverse of a bar of s into z bar of s. So what is our convolution theorem states that whenever we want to find out L inverse of a bar of s into z bar of s, so then this can be written as f of t star g of t. So now by using this statement here, our task is first we have to find out f of t and then we have to find out the g of t value here. So how can you find out f of t and g of t here? We know that f of t is equal to, we can find out this f of t value like this, L inverse of f bar of s, and g of t, if you apply the inverse Laplace transform for g bar of s, then we can get our g of t value. So after finding that f of t and g of t, then we can go for the definition of convolution product. So this can be written as integral 0 to t f of u into g of t minus u du. If you evaluate this integral, then we can complete our problem here. Okay, so now which is of the form, so now whatever we have reduced this function in this form, this is of the form L inverse of f bar of s into z bar of s. So we can consider this as f bar of s and this as z bar of s. So here f bar of s is equal to s by s square plus a square, and we can take this function as g bar of s is equal to 1 by s square plus a square. Now for these two functions you apply the inverse Laplace transform, then you will get our f of t and g of t value here. So L inverse of f bar of s, that is L inverse of f bar of s, what is the value we consider for f bar of s? S by s square plus a square. L inverse of s by s square plus a square, we have the standard formula, that is cos at. You consider this value as f of t for some time, and now similarly take this, you apply inverse Laplace transform, then get the value of g of t here. So now L inverse of g bar of s is equal to L inverse of 1 by L inverse of 1 by s square plus a square. 1 by s square plus a square, we can take it as 1 by a into sin at. This is also the standard formula in the inverse Laplace transform. So L inverse of 1 by s square plus a square is equal to 1 by a into sin at. So whatever the value we got after applying the L inverse for g bar of s, you consider that value as g of t. Now we got f of t value and we got g of t value. So now we are ready to apply this convolution theorem. Now by using this convolution theorem, what is the statement here? L inverse of, so L inverse of the given function, that is f bar of s into g bar of s, is given by f of t star g of t. But by using the convolution product, we can take f of t into integral 0 to t into f of u into g of t minus u du. So this is equal to integral 0 to t. What is our f of t here? Cos at. So we got f of t is equal to cos at, and g of t is equal to, we got 1 by a into sin at. So now we don't want this f of t value, we want f of u value. So just replace t with u here. You will get cos au into g of t. We got this value, but here we want g of t minus u. So replace t with t minus u. You will get this value here. Now simplify. You take that 1 by a outside. So now once if you take this 1 by a outside, you will get cos a, which is of the form cos a sin b. So cos a sin b. So we have in this form cos a sin b. We have the formula for this 1 by 2 into sin of a plus b minus sin of a minus b. Now you consider this au as capital A and you consider this entire value as b. Now you apply this formula. So you will get sin of a, that is au, plus b, that is at minus au, minus sin of a minus b, that is au. You apply. So this is at minus au. You multiply with minus, so you will get minus at, minus of minus plus au. Now simplify this. So this au and this au gets cancelled. You will get at minus sin into au plus au. You will get 2au minus at. Now apply the integration here. So 1 by 2a integral of sin t, integral of sin x. So this can be written as, so here we don't so here we are applying the integration with u, but here we don't have the u variable here, so this becomes a constant. So you write down this constant outside. So after taking this one, you will get, suppose this is sin at into du. So here we are applying the integration with respect to u, but here we don't have the function in terms of u. So we can take this one as sin at into 1. So we can take sin at integral 1 into du. So this can be written as sin at integral of 1 into dx. We can take u. So that we have applied here. And same here also you find out this integral of sin. So in this we are having the term, the variable u. So integral of sin, you take that formula, integral of sin is equal to minus cos this. You once again you apply the derivative of this. You write down that value in the denominator here. Now you substitute this limits here, upper limit and lower limit, and simplify. We can get our required value here. So after simplification and cancellations, so this gets cancelled. You will get only t into sin at by 2a. So finally we got this value here. So whenever we want to apply this convolution theorem, we have to remember some important points. The first one is we have to take the function as the product of two functions. That is the first point, and then apply this. So you whatever the function we have expressed as the product of two functions, you consider one function as f bar of s and you consider the another function as g bar of s. So by using this f bar of s, get the value of f of t, and by using this g bar of s, get the value of g of t. Then use the convolution theorem, apply the convolution product of f of t star g of t. So use the definition of convolution product and then evaluate that integral. We can get our required value here. So whenever we want to find out the L inverse value, inverse Laplace transform, whenever the function has a product of two functions, then in the inverse Laplace transform we can find this value by using this statement of convolution theorem. So that is the flexibility we are having in the inverse Laplace transform. This is used to find out the inverse Laplace transform for the product of two functions. Let us take one more example here. L inverse of s square by s square plus a square into s square plus b square. So this is our f bar of s. F bar of s is equal to s square by s square plus a square into s square plus b square. This is our function. Now what we have to do is we have to convert this function as a product of two functions. How can you write this one as s square? That can be written as s into s. So one s I will take for the first factor. So s by s square plus a square. Another s I will go for the second factor, s square plus b square. So you consider this as f bar of s and this as g bar of s. These two are product. So this is our first one. We have to go for the convolution theorem. So this is L inverse of, and so this can be written as this one. Now this is of the form L inverse of f bar of s into g bar of s. You consider this as f bar of s, you go for the g bar of s. So here f bar of s is equal to s by s square plus a square, g bar of s is equal to s by s square plus b square. Now by using this f bar of s and g bar of s, get the value of f of t and get the value of g of t by applying inverse Laplace transform. So L inverse of f bar of s is equal to L inverse of s by s square plus a square. We have the formula cos at. So you consider this cos at as f of t, and similarly go for this g bar of s. So L inverse of g bar of s is equal to L inverse of s by s square plus a square b square, that is cos bt. You consider this as g of t. Now we got both f of t and g of t. Now we are ready to apply this convolution theorem. So by using convolution theorem, what is our convolution theorem? Says that L inverse of f bar of s into g bar of s is equal to f of t star g of t. So this can be written as by the definition of convolution product integral 0 to t f of u into g of t minus u into du. So directly we can take L inverse of s by s square plus a square into s by s square plus b square is equal to integral 0 to t. This is equal to integral 0 to t f of t. We know the f of t, that is cos at, but here we want in place of t, here we are having u, so this can be written as cos au into cos g of t minus u. We got g of t is equal to this, replace t with t minus u, we will get cos b of t minus u du. Now then complete this integration by using this formula. So this is of the form cos a into cos b. Cos a cos b is equal to 1 by 2 into cos of a plus b plus cos of a minus b. So you consider this as a and you consider this as b and substitute that values in that formula. We can get our required value here. Then find out the integration with respect to u. We will get this value. In this you substitute the upper limit and lower limit. Upper limit in place of u, we have to replace u with t upper limit and u with 0 lower limit here. Now simplify this, we can get our required value here. So after simplification, after the cancellations, finally we get a sin at minus b sin bt by a square minus b square. So this is the way we can apply this inverse Laplace transform using convolution theorem. So with this we have completed how to apply the convolution theorem to find out the inverse Laplace transform of product of two functions. So this is the last concept in the convolution theorem. Now in the next video, so we are perfect with the Laplace transform and we are perfect with the inverse Laplace transform. Now by using both Laplace and inverse Laplace transform, we are going to discuss the application of Laplace transform in the next video. So in the beginning, in the introduction of this unit, we have taken some applications where we can use this Laplace transform. So we are having how to find out the solution for the given differential equation, initial value problems. So differential equation will be given, along with this differential equation initial conditions will be given. So by using these initial conditions for the given differential equation, by applying the Laplace transform, we are going to find out the solution here. So we will discuss the procedure and we will take some problems to find out the solution for the given differential equation by using Laplace transform technique in the next video. Thank you.